So if you've ever dipped your toes into magnetism, you probably know that calculating magnetic fields can get, well, pretty complicated. But what if I told you there's an elegant shortcut, a really powerful tool that can just slice right through some of the toughest problems? Well, there is. It's called Ampere's law, and today we're going to pull back the curtain and see how it works. So here's the game plan. We're going to start with the absolute basics, the link between currents and magnetic fields. Then we'll introduce the star of the show, Ampere's law itself. After that, we'll walk through exactly how to use it step by step. We'll even tackle a classic problem with a long wire. And finally, we'll talk about why this law is all about one thing: symmetry. Okay, first things first. Where do magnetic fields even come from? Well, the simple but kind of profound answer is moving charges. Anytime you have an electric current, which is really just a bunch of charges flowing together, you get a magnetic field. It's the fundamental connection, the bedrock that links the worlds of electricity and magnetism. And this image here, it shows it all perfectly. Imagine that current, the I, is a wire poking straight out of your screen. What happens? It creates a magnetic field, B, that swirls around it in these perfect circles. And if you want to know which way it's swirling, just use the good old right-hand rule. Point your thumb in the direction of the current, so at the screen, and your fingers will naturally curl in the exact direction of the magnetic field.
So we know the field is there, but how strong is it at any given point? Well, you could use something called the Biot-Savart law. It's the brute force method that works for any situation. But honestly, the math can be a total nightmare, a real grind. That's why we need a better way, a more clever approach for certain problems.
And that smarter approach, that's Ampere's law. This is the hero of our story today. And if you studied electricity, it's kind of like the magnetic cousin of Gauss's law, another awesome tool that banks on symmetry. It's a brilliant shortcut that turns some really gnarly problems into something surprisingly simple.
So what's the big idea? Conceptually, Ampere's law says this. Imagine you take a walk in any closed loop you want. As you walk, you add up the magnetic field that's pointing along your path. The law states that the grand total you get is directly tied to the amount of electric current that's poking through the surface of your loop. It's this really cool connection between what's happening along a path and what's happening through it.
We call this imaginary loop an Amperian path. See path M on the slide? It completely surrounds the current, I. Ampere's law tells us that if we walk along that whole path and sum up the field, the result is all about that current inside. But now, look at path N. See how it doesn't actually circle the current? For that path, the law says the grand total is 0, nothing.
And here it is, in all its mathematical glory. Let's break this down real quick. That circle on the integral sign just means we're going all the way around a closed loop, our Amperian path. The B.dl part means we only care about the piece of the magnetic field that's running parallel to our path at every step. And all of that equals a constant, mu0, times the most important part, I enclosed, which is the total net current that punches through our loop.
Okay, so that's the theory. But how do we actually use this thing to solve a problem? Let's lay out a practical, step-by-step strategy.
All right, here's your 6-step battle plan. First, and this is the most important one, you have to look for symmetry in the problem. If there's no symmetry, Ampere's law is probably not your friend. Then, figure out the direction of the B field, choose a really clever Amperian path that matches that symmetry, find the current inside your loop, calculate that integral, and finally set the two sides equal and solve for B.
You know, the real magic here is that I enclosed. This is what makes Ampere's law so powerful. Any currents flowing outside of your chosen loop, I don't care how big they are, they contribute exactly 0 to the final calculation. You literally just ignore them. It simplifies things massively.
But what if you have a bunch of different currents inside your loop? How do you add them up? Well, we use another right-hand rule. Get your right hand ready? I want you to curl your fingers in the same direction you're walking along your Amperian path. Now look at your thumb. Your thumb is now pointing in what we call the positive direction. Any current going with your thumb is positive, any current going against it is negative.
Let's give it a shot. For the path on the left, we curl our fingers counterclockwise so our thumb points out of the screen. That 2 amp current is also pointing out, so it's positive. The net current is just plus 2 amps. Easy. Now for the path on the right. Same thing. Thumb points out. The 7 amp and 5 amp currents are coming out, so they're positive. The 3 amp current is going in, so it's negative. So the net enclosed current is just 7 plus 5 minus 3,
which is 9 amps. Simple as that.
All right, time to put all this theory into practice. We're going to take our 6-step strategy and use it to solve the most classic of all magnetism problems, finding the magnetic field around a long, straight wire carrying a current.
Step 1, we've got cylindrical symmetry. Step 2, because of that symmetry, the B field has to form perfect circles around the wire. So for step 3, what's the smartest possible Amperian path we can choose? A circle, of course. A circle of radius r centered on the wire. Now, why is this so clever? Because on this path, the magnetic field, B, always has the same strength, and it's always pointing in the exact same direction as our path.
And because we were so clever with our path, the math just falls apart. It becomes super simple. That complicated integral on the left side of the equation just turns into B times the length of our path, which is the circumference, 2 pi r. The enclosed current on the right side is just the total current in the wire, I. We set them equal, solve for B, and boom, we get this famous result. The field gets weaker the farther you get from the wire.
Okay, that was for a point outside the wire. But let's say we have a thick wire, and we want to know what the magnetic field is doing inside the conductor itself. All we have to do is draw a new Amperian loop, this time inside the wire, at a radius r that's smaller than the wire's total radius a.
Now, here's the crucial little twist. Because our loop is smaller than the wire itself, we're not enclosing all of the current anymore. We're only enclosing a fraction of it. If we assume the current is spread out evenly, the amount we enclose is just proportional to the area of our loop. So the enclosed current is the total current, I naught, multiplied by the ratio of the areas, which is just r squared over a squared. So we take this new, smaller enclosed current and plug it back into Ampere's law. The left side is still B times 2 pi r. We solve it all for B and we get this really fascinating result. The magnetic field isn't constant in here. It actually starts at 0 at the very center of the wire and then grows in a straight line, getting stronger as you move outwards towards the edge. And check out this graph. It just pulls it all together so nicely. You can see the magnetic field increasing linearly, in a straight line, from the center of the wire out to its edge at radius a. Then, the moment you step outside the wire, it starts to drop off, getting weaker as 1 over r, just like we found before. It's a complete picture of the magnetic field, all thanks to Ampere's law.
So let's just take one final step back. We've seen just how powerful this law is, but it's really important to know where it fits in our physics toolbox. When should we reach for it, and when should we leave it on the shelf?
Here's the best way to think about it. Ampere's law is like a surgeon's scalpel. It's incredibly precise, elegant, and lightning fast for problems that have a ton of symmetry. Think infinitely long wires, solenoids, toroids. The Biot-Savart law, on the other hand, is more like a sledgehammer. It's universal, it'll always get the job done, but it can get messy. You need that sledgehammer for the problems that don't have that clean symmetry, like a short wire or maybe a square loop of current.
This quote from our source really just hits the nail on the head. The entire trick to using Ampere's law, the whole secret, is being able to find a special path where that complicated integral becomes super easy to solve. If you can find that path, the law is your absolute best friend.
So today, we've seen how Ampere's law gives us this incredible intuitive shortcut for these perfect, idealized situations. But it does leave us with a big final question, doesn't it? What happens out here in the real world where things are messy and perfect? Infinite symmetry just doesn't exist. How do we handle those more complex systems? And figuring that out, well, that's the next chapter in your physics adventure.